Hi, my name is Ian, and today we're going to take the exciting concept of transformations in grade 11 and deal with it. Now, what are transformations? A huge word. Two bits, to transform. Let's have a look at the word on screen. It is to transform. What are we going to do? We're going to take shapes and move them, rotate them, reflect them, and also resize them. And that's what transformations is all about. Now, where in the real world do you think we would use transformations? Well, one great use is in the industry for TV, where we have cartoons. How do you think Mickey Mouse, for example, moves across the screen? In the old days, we would have to draw Mickey Mouse 20 times to get him to move a few inches. But these days, the computer does the transformations for us. And we say, take the Mickey Mouse shape and move it across the screen. A glide transformation. That's one of the uses for transformations in the real world. Right, let's get started. The key concept that we have are reflections, and that is the big one in grade 11, are reflections around the y-axis, the x-axis, and the line y equals x. In addition to this, we've got to remember that in grade 10, we had glide transformations or slide transformations. Whichever term was used means almost the same. It means moving left or right, up or down. We're also going to tackle the concept of rotations around the origin with increments of 90 degrees. So 90 degrees, 180, 270, 90, both clockwise and anti-clockwise. Let's look at the first couple of reflections. Well, let's start off with two pieces of cardboard over here. If I have my y-axis running horizontally, not horizontally, vertically as we know it does, if I was to reflect it, it would reflect like it does in a mirror. So that the inside bits would still be there, the right angles would be close together, and these little angles would be far away. They would reflect around the vertical axis. Now, what's actually happening? Let's have a look at that algebraically. Around the y-axis, we have that xy becomes minus xy. Let's look at that with our cardboard cutout again. There was our triangle, and what is happening is the x values are changing. The y values aren't changing at all. The right angles, the y values are staying exactly the same. So what happens? It becomes minus xy. Now, if it was on the negative side and it was reflecting around, for example, it was negative 2, 3, it would become 2, 3, and vice versa. Right, let's have a look at another reflection. That's around our horizontal axis or our x-axis. Here we have another shape. If it was to rotate around the x-axis, what is changing? Are the y values changing? Oh yes. Are the x values changing? Definitely not. Let's have a look at that again. And what we're going to be doing is concentrating on this vertical point over here, this point up here. The x value doesn't change, but there it goes, all the way down. So similarly to our reflection around the y-axis, a reflection around the x-axis, the y values change sign. Let's look at that algebraically. reflection around the x-axis, our xy becomes x minus y. Now that's well and good, and that's pretty easy to remember. But now we've got this oblique line, or slanted line, the line y equals x. And I'm going to pull my screen down a little bit so that we can draw it. If I have a Cartesian plane, I'm going to put in my line y equals x over there. Now remember, on that line, you've got the point 0, 0, 1, 1, 2, 2, 3, 3. Now, if you were going to reflect around that line, whatever was on one side is going to reflect exactly the same on the other side. I'll give you a point and show you what I'm talking about. For example, if this was the point 5, 1, if that were to reflect around the line y equals x, the reflection line, the distance from 5, 1 to the line y equals x would be exactly the same as the distance to its reflected point. So this would be the point over here, also at 90 degrees, will be the point 1, 5. The point 5, 1 became the point 1, 5. Algebraically, what do you think it is? xy becomes, you've got it, yx. Absolutely correct. xy becomes yx. Let's have a look at that with another shape. Across the line, y equals x. There it is. If it was to reflect, there we go. xy becomes yx. Now the one rotation, the one reflection, which I'm going to deal with now, is rotation. Now in grade 11, we only deal with rotations of increments of 90 degrees, both clockwise and anti-clockwise. Now on screen at the moment, I'm sketching a Cartesian plane, and I'm showing you first in yellow, and that direction is anti-clockwise, and the opposite direction is clockwise. Now when you get to matric, we have rotation of any number of degrees, and there are two formulas on the formula sheet. One for anti-clockwise rotation and one for clockwise rotation. We don't have to worry about the formula at the moment because we're doing, as I said, increments of 90. Let's have a look. If I was to take a point, and I'm going to use the point 5, 1, and I was to link that to the origin. Now, just by the way, in grade 11, we only rotate around the origin. We also only rotate around the origin in matric. And those of you who are doing AP maths, you might rotate around any point on the Cartesian plane. That gets really, really exciting and quite difficult. Right, back to this. Here we have the point 5, 1. If I was going to rotate it by 90 degrees anti-clockwise, it would go from the first quadrant 90 degrees into our second quadrant, and it would land up being the point 1, 5. Minus 1, 5. So 5, 1 becomes the point minus 1, 5. Yes, the x's and y's swap over, and the new x gets a negative. Let me change color pens and write that algebraically. So what we have is we have xy becomes negative y x. So this is rotation of 90 degrees anti-clockwise. Now I know that some of you have heard the term counterclockwise, and that's a valid term, but that is what the Americans use. But here in South Africa, we follow the European standard for mathematics, and we use the term anti-clockwise. Right, let's have a look at this. I take a point, and I'm going to use my cardboard cutout, or I take a shape, and I rotate that 90 degrees clockwise. The shape follows like the wheel of a car would follow. So the pointed bit, which is pointing outwards at the moment, would point upwards over there. So it's very dissimilar to a reflection. Now what would happen if I was to do it by 180? Well, I could do it by 90 first, and then by another 90, and then I would have a rotation of 180. Please observe, and it's quite apparent with these cutouts, is that this little part over here has rotated around, and from pointing upwards, it is now pointing downwards. Let's have a look at the algebraic form for rotation around the origin of 180 degrees. I'm going to start with my usual point, the point 1, 5. Why do I use the point 1, 5? It's because it's a nice point. That's all. Nothing else other than that. Now, 1, 5 goes 90 degrees and becomes minus 1. Sorry, I've made a mistake over here, and I'm sure that you are shouting at me through the TV screen. That is the point 5, 1. This would become minus 1, 5. If I was to send that on another 90-degree rotation, my point now would become minus 5, minus 1. Let's have a look at that algebraically. And I'm going to do it in 2 steps and then condense it into 1 if that's the way that you would prefer to remember it. So I started off with my point xy, and that became minus yx on my first 90 degrees. I then flipped it over another 90 degrees, and what happens? It has exactly the same transformation, and it lands up being minus x minus y. Goodness me. Exactly the same as our original point, but with opposite signs. So, you might like to remember it as a shortcut, a 180 degrees rotation around the origin in an anti-clockwise direction, goes from xy to minus y minus x. Now how about if I did a 180 in a clockwise direction? Let's slip slightly back up the screen and have a look at the last diagram that I sketched. If I was to take my 180 degrees there, yes, I would land up at exactly the same point. So, my summary, 180 degrees, that can be either clockwise or anti-clockwise. Just abbreviating it because the side of the screen is quite close. All right, are we happy with that? Let's have a look at if I was going to do a rotation of 90 degrees clockwise. I'm sure some of you are saying, but what if I started in the second quadrant and it had to rotate into the first? Okay, I'll do that now. All right, so we start over here with something in our second quadrant, and I'm going to choose the point minus 1, 6. for purposes of this demonstration. So minus 1/6 rotates 90 degrees and it's going to go in a clockwise direction. What is going to happen? And I'm going to rub that line out and just do it properly so it really is 90 degrees so we can see that correctly. That becomes the point 6, 1. All right, so let's summarize that and see what's happened to our point minus 1/6 as it transformed to 6, 1. Well, from xy, what happened? It became y minus x. Swapped over and the x changed sign. Now, if you're thinking, goodness me, there's so many rules, I'm going to get confused, what I do almost every time I do this is do a little sketch similar to the one I've done on screen. Quickly, and I can see exactly what is going to change. Are the x's going to change? Are the y's going to change? Which of the signs are going to change? So you don't have to commit this all to memory. I know that some of us, like me, often get confused when we have to commit lots of stuff to memory. So remember, just do yourself a little sketch. All right, what we've dealt with is we've dealt with our reflection around the y-axis, our reflection around the x-axis, our reflection around the line y equals x, and our rotation, clockwise and anti-clockwise, of 90 and 180. Now, one of you out there is saying, but what about 270? Let's have a look. If I was going to rotate, and once again, I'm going to use my point 5, 1. If I was going to rotate 270 anti-clockwise, I would have to go all the way around. And what is that? That's exactly the same as 90 degrees clockwise. So we don't have to learn about a 270. We can use our knowledge and talk about it as a opposite rotation of 90 degrees. Just something to keep in the back of your memory banks. Sometimes one day it'll pop up and be useful. Back to the sketch, our point 5, 1 became 1 minus 5. So if we were worried and we really wanted to learn all these things off by heart, 270, our xy becomes y minus x. Okay. All right. The last transformation that I'm going to do is quite a complicated one in terms of size. What I'm going to take is I'm going to take a big square and make it small, and then compare the areas, and that's a typical question, or a small triangle and multiply it by what's known as a scale factor. Just means I'm multiplying it by some number. Make it big, and then I'm going to compare the areas. Let's have a look at a little cardboard cutout. What I could start off with is I could start off with a square sides 10 and 10. And if I was going to multiply this by a scale factor of 2, voila! I'm doubling the length of each side. You can see that it becomes 20, and you can see that it becomes 20 across there. So I've multiplied it by a scale factor of 2. Can you tell me what's happened to the area? I'll give you a little hint. 1, 2, 3, 4. The area has increased fourfold. The area has increased 4 times. Now, how come if I multiply it by 2, will my area increase by 2 squared? Oh, that's the hint. Yes, area as you remember, is in square units. So if you were going to multiply the sides by 3, you'd have to increase the area, or the area would increase by 3 squared. Let's have a look at another one. Here I have a large rectangle, 20 by 25. Now, if I multiply that by a fraction, a scale factor, which is a fraction, I could get a little rectangle, which is 4 by 5. What was my scale factor that I multiplied the blue rectangle by to get the red one? Well, my side went from 20 to 4, and my length went from 25 to 5. Yes, I multiplied it by a scale factor of 1 over 5. So to go from big to small, I multiplied by 1 over 5. To go from small to big, I would have had to multiply by 5. Can you think of what the area is going to increase if I went from red to blue? By what factor? I multiplied the sides by 5, which means I'm multiplying the area by 5 squared, or 25. Yes. How about if I'm going from blue to red? I'm decreasing the sides by a factor of 5, so I'm decreasing the area by a factor of 1 over 5 squared, which is 1 over 25. Quite a difference. Let's pop that down for a moment and have a look on screen. Here on screen, I'm going to do a Cartesian plane, and I'm going to draw a square so that we can see how this works in action. Okay, this will be our point 1, 1. How long do you think we should make the sides? All right, let's make them a length of 2. So this point would be the point 3, 1. This point over here would be the point 3, 3. And the last point would be the point 1, 3. So what I've got is I've got my 4 vertices of a square. Now what I'm going to do is multiply by a scale factor of 2. I'm going to multiply a scale factor of 2. Now you might have touched on this last year, but if you didn't, I'll write down the algebraic transformation for you. In this case, every xy point is going to become 2x, 2y. Quite easy. Just multiply every x and every y by 2, and let's see where we go. Well, my 1, 1 will land up being the point 2, 2. My 3, 1 will land up, yes, you guessed it, 6, 2. My 1, 3 will land up being 2, 6. And my last point, 3, 3, will land up being 6, 6. And if I join those together, you can see the square has not only shifted in essence, but it is grown. Every side has grown by a scale factor of 2. Let's have a look at the area. Well, in my first little diagram, the side over there was 2 units in length, and it was a square. So my area of my first transformation was 2 squared, or 4. In my green square, the length of my side was 4. So my area will be 4 squared, which is 16. So if I look at the ratio area small I'm just using that notation because it's quite easy to understand, to area big, I have the ratio 4 to 16, and we all know that we have to simplify our ratios. I'll get the ratio 1 to 4. So what has happened? I multiply every side by 2, and my area increases by 2 squared. Let's have a look at another cutout. Here I have a green triangle with sides 10 and 20. Now, if I was going to multiply the sides by a half, I would get the little yellow triangle with sides 10 and 5. What do you think has happened to the area ratio green to yellow? Remember, it was a half that I multiplied the sides by? Yes, a half squared, which is a quarter. So this little yellow triangle, if we were to chop up 4 of them, they would fit inside that green triangle. Now, for some of you who may be skeptical, let's work out the area of this triangle. Well, we know the area of a triangle is half times the base times the height. So a half times 10 times 20 gives us 100 square units. Let's have a look at the little one. A half times the base times the height. A half times 5 times 10 to give me 25. 25 square units as opposed to 100 square units. Yes, it is decreased by a quarter. Why? A half squared is a quarter. Big one, little one. Scale factor, a half. Areas, 4 to 1. What we're going to have a look at now is a couple of questions so that you can see how this is asked in a testing situation. Right, question 1. Here they give us a diagram and they tell us that A is negative 4, 5, and we can see that clearly on the diagram. A is negative 4, 5, B is negative 5, 3, and C is the point negative 2, 2. And those 3 points form the triangle ABC. Let's have a look at the question. They ask us to reflect about the y-axis forming A dash, B dash, C dash. Now, before I go any further, let's have a look at this notation. What is this thing of dashes? Well, if I have the point A and I want to transform it anyhow, it becomes A dash. That means it's had one transformation. If I take A dash and I transform it somehow, yes, it becomes A double dash. And if you wanted to transform it again, it would become A triple dash. A, one transformation, A dash, 2 to A double dash, and 3 to A triple dash. Now, this is what could happen in a test, is you get a shape or a line or a point, and it's reflected once, reflected twice, rotated, and see where you land up. So A goes to A dash, to A double dash, and to A triple dash. Okay, let's go back to the question, and let's see what the question is actually asking us. Here they ask us to rotate it around the y-axis. We must draw the image, and we must clearly label the new vertices. What is the point, what does the term vertices mean? Well, one vertex, many vertices. And a triangle is 3 vertices. Each corner is a vertex. Just another word for a corner. Let's go to the diagram and see how we're going to reflect this around the y-axis. Now, if you've forgotten the rule, all we have to do is to pretend that there's a mirror down the y-axis and we're taking this little shape, this little triangle, and all we're going to do is reflect it. Let it have a look at itself in the mirror and draw it on the Cartesian plane. Well, how many units across is it? A is minus 4 units across, so it must go 4 units across and land up there. Remember, when we reflect around the y-axis, the x changes and the y doesn't change at all. So our point A dash was minus 4, 5, becomes 4, 5. Let's do the same with point B. Well, point B is minus 5, 3. Once again, we remember around the y-axis, the x changes sign. So it's going to become the point 5, 3. Let's put that on the Cartesian plane. And there we go, using our notation, B dash becomes 5, 3. Point C. Point C is minus 2, 2, reflecting around the y-axis. The y's don't change, the x's do. That becomes minus 2, 2. Remembering our notation, C dash becomes the point 2, 2. What I have to do now is to join my vertices up. And what I've done is I've taken the point ABC, the triangle ABC, and I've reflected it around the y-axis to become A dash, B dash, C dash. Have I clearly labeled the vertices, each point? Yes, I have, by using the correct notation for points in a Cartesian plane. Well, that's those 3 marks in the bag. Let's move on. Same question, another subsection. Right, now they want us to take A dash, B dash, C dash and rotate it through 180 degrees to become A double dash, B double dash, C double dash. And we have to draw it on the axes above. Now I'm going to go back to my previous picture so I can take A dash, B dash, C dash and make it rotate through 180 degrees to become A double dash, B double dash, C double dash. Right, there we go. 180 degrees. Okay, what happened with 180 degrees? It is going to rotate and is going to land up there. Now, for those of you who forget, if we have 180 rotation, what is going to change? Well, the xy is going to become minus x minus y. Okay, I'm going to rub out my yellow arrow and draw in the new triangle in yellow. All right, 2, 2 would become the point minus 2, minus 2. So what is that point? That is the point C double dash. And once again, I will label the points accurately. Becomes minus 2, 2. Minus 2, minus 2. My point B was 5, 3. So rotating that around the axes, I will get minus 5, minus 3. So I have minus 5, minus 3 is my point, and that is B double dash. Having a look at our point A, I'm going to go from 4, 5 all the way around to -4, -5, which is over here. So there I have my point A double dash, and that is -4, -5. And now I need to join up the sides of the triangle. There we go. I know that some of you are saying, I've been working anti-clockwise, and you prefer to work clockwise. Remember, with 180, there's no difference. Part C of this question asks us to describe a single transformation. One single transformation that would take ABC into A dash, A double dash, B double dash, C double dash. If we remember what happened, is we landed up, and I'm going to go back to my original diagram. We landed up with A double dash, B double dash, C double dash down here in the 4th quadrant. They want a single transformation that will take my blue triangle and make it become yellow. Now what I'm going to do is I'm going to list the points so that I can be absolutely certain what happened. Some of you are not going to be required to do that, and that's absolutely fine. If you can see the single transformation, write it down straight away, go for it. I know that the point A, let's just go back and double check, the point A was -4, 5. And what actually happened to the point A? It became -4, -5. Well, let's check on point B. B was the point -5, 3, and it became -5, -3. So it was -5, 3, and it became -5, -3. I'm sure some of you are noticing the transformation that's happened. Point C, going back to the original sketch, point C was -2, 2. Point C was -2, 2. And it became -2, -2. I know that you've got it. The x's have stayed the same, and the y's have changed to -y. So, what are we going to do? We need to write this transformation out properly. So, our transformation, xy, what happened? Well, the x's stayed the same, and the y's got a negative. So, what happened? From ABC to A double dash, B double dash, C double dash, what we could have done was reflect it around the x-axis. Yes, all this is a reflection about the x-axis. Let's check how the question wanted us to express our answer. They wanted us to put it in words. So, by writing it, a reflection around the x-axis, we would then get full credit for that question. I'm sure you're all happy with that. What we're going to do is we're going to move on to another question. Now in this question, they take a line PQ, and it is really nicely shown on the grid. P is the point minus 7, 1, and Q is the point minus 3, 6. And we're now going to rotate, reflect, maybe even glide transform this line segment PQ, and let's see what happens. Right, here we go to question 2. Now, here we're given a line segment PQ, with P at minus 7, 1 and Q minus 3, 6. Now they're going to take this line and they're going to do glide transformations, rotations, reflections around axes. Let's actually see what they've got. But first, just to refresh your memories, with a glide transformation, if they wanted you to change the x value, it would be x plus 2 or x minus 2. And if they wanted you to change the y value, it will be y minus 5 or y plus 7. So whatever happens on the x's is going to influence it horizontally. Whatever happens on the y's is going to influence it vertically. Let's have a look at the question. Here they want us to move it to a new transformation of x minus 3 and y plus 2. So what's going to happen? My x is going to go down 3 and my y is going to go up 2. All right, 1, 2, 3, 1, 2. That is where my new P is going to be. Down 3, up 2. Similarly, it's going to happen to my Q. My value of Q is going to go down 3, 1, 2, 3, and go up 2. Down 3, and my Y is going to go up 2. The question is asking me for the new coordinates. Now, if you didn't want to draw it on the axes, you wouldn't draw it on the axes. You would just calculate this in your head. Write down the answer. No working required. P has gone from minus 7, 1. P was minus 7, 1. Let's drop the x's down by 3. So P dash would be negative 10. And the y's are going to go up by 2. So 1 plus 2 gives us 3. Have a look at Q. What was Q originally? Minus 3, 6. Q was minus 3, 6. And all we're going to do is we're going to subtract 3 from that. So we'll get minus 6. And our y's are going to go up 2. So we'll get 8. So from P minus 7, 1, we do a glide transformation. X's go down 3 and y's go up 2. So it becomes minus 10, 3, and the Q becomes minus 6, 8. Let's just double check that on our sketch to make sure that we're absolutely correct. Well, yes, P minus 10, 3. Absolutely correct. We're 100% with that. And our Q value, our new Q over there, all right, just extending that, and that would give us about an 8 over there, should be minus 6, 8. Absolutely correct. Spot on. Glide transformation. Let's move on to the next subsection. Here they take PQ and they want us to rotate it 90 degrees through the origin. Now, in this question paper, they haven't specified clockwise or anti-clockwise. Here's the trick. Mathematicians always take anti-clockwise as being positive and clockwise as being negative. A little diagram on the side to help. If we were going that way, it's positive, and if we're going the other way, it's negative. So rotation of 90, you would interpret that as positive and anti-clockwise. So let's go back and do a little sketch, because I can't remember whether the minus x became a y, the y became minus x, or what happened. So let's do a little sketch. If we started with our point 5, 1, and we rotated it 90 degrees anti-clockwise, it would become minus 1, 5. So our rotation transformation xy becomes minus y x. xy becomes minus yx. Right, back to the question. P is minus 7, 1. So P is minus 7, 1. What is that going to become? Well, P dash is going to become minus 1, minus 7. Let's get the coordinates for point Q. Q is the point minus 3, 6. So minus 3, 6. There we go. Q dash, and look at the notation, we're doing it correctly, becomes minus 6, minus 3. How useful was that little diagram down below? I remember to do that every single time I'm doing a 90 translation. It really, really helps. Okay, those two bits are done. On to the next subsection. Now what we have to do is a reflection around the line y equals negative x. We haven't discussed that before. Y negative x. I'm going to move down to the bottom of the page and we can discuss it. If I have a Cartesian plane over there, my line y equals negative x would be that line over there. Slope of negative 1 running through the origin. So take a point, and I'm going to work in my second quadrant. I would take a point, for example, negative 1, 6. And I would reflect it around this axis. Well, I know that my distance into the axis, 90 degrees, must be the same as my distance out of there also at 90 degrees. That distance must be the same as that distance. And what would my new point become? Well, we become minus 6, 1. Let's write that on the side. Minus 1, 6 translates into minus 6, 1. Goodness me, what's happened? The minus 1, which was x, becomes the y, but it loses its minus. And the 6 that was the y gains a minus, it becomes the x. Right, so what we're going to do is we're now going to write this algebraically. My x became minus y, my y became minus x. So, my xy point translates and becomes minus y minus x. Now, if we go back to our little sketch and we have a look at our line y equals minus x, it'll become quite apparent why this transformation is as it is. The equation of this line is y is equal to minus x. So whatever was y becomes minus x. And if I change the subject to the formula, I get that x is equal to minus y. So whatever was x becomes minus y. It's quite easy when you think of it that way. Right, let's go to the top and answer the question. The point P is the point minus 7, 1. So let's write that down. P is the point minus 7, 1. And that is going to translate and become P dash. Remember, what was x becomes minus y, and what was y becomes minus x. So that becomes the point minus 1, 7. Let's do the same for point Q. Q is the point minus 3, 6. So Q is the point minus 3, 6. That's going to become Q dash. The y gets a negative and pops up front, becomes the x. The x gets or loses a negative and pops the back to become the y. Let's just refresh for a moment. We have xy becoming minus y minus x. Also, our notation, P, transformation, becomes P dash. Please make sure that you do your notation correctly. When the marker is marking your work and wants to give you credit, he needs to know that you know what's going on. That's why notation is absolutely vital for all of us. Let's move on. Here is question 3. Now, question 3 has a whole bunch of colorful triangles labeled P, Q, R, S, and T on it. And what we're going to need to do is to describe transformations in words. So this is where you're going to have to use the words like rotate, 90, 180, 270, clockwise, anti-clockwise. Use words like reflect around the y-axis, or around the x-axis, or around the line y equals x, or the line y equals minus x. Sometimes, if you're not sure, it's useful to list the points, as we did a few minutes ago, and then just check what the translation is. Let's have a look at the question. They want us to go from P to R. What is the translation if we go from P to R? Now, it's not really obvious what's happened. If I draw a line from there to there and from there to there, I'm sure a lot of you are going to see that it is a rotation of 90. Now, how did I know that it was not a reflection? Well, if it was a reflection, it would be almost the same shape, just upside down. If we have a look at this triangle, if it was a reflection, like that, the reflection would be like that. It's obviously not. So what are our only options? If it's not a reflection around the line y equals 0 or the x-axis, let's have a look at our rotation of 90. Now, I've got negative 90 or 90 degrees clockwise. I'm going to write down a couple of the points and double check. The point P is the point 7, 6. The point P is the point 7, 6. And that goes down to a similar point, 6, negative 7. So in R, it is 6, negative 7. I'm sure that you can see that the translation xy to y minus x has occurred. And that is our rotation of 90 degrees clockwise. Yes, some of you might like to call that a rotation of 270 degrees anti-clockwise? And that answer is perfectly correct. Two answers, same thing. Some of you might like to talk about positive 270 degrees or negative 90 degrees. I would suggest, however, that you stick to the words clockwise and anti-clockwise to describe positive and negative. Let's have a look at our next one. From P to T. Well, from P to T, it's going across the y-axis. Let's have a look at the triangles just to make sure that the shapes haven't done something else strange. Well, this side over here is 1, 2, 3, 4, 5, 6 units long, and so is that side. So the outside bits are the same length. The same idea is if I took my cardboard cutout and I reflected it around the y-axis, the outside bits are the same length, the top bits are the same length. So what is going to be happening if I go from there to there? I'm reflecting around the y-axis. I'm, however, going to list one point on P and 1 point on T, just to double check that. Well, I'm going to use the same point on P, the point 7, 6. And as it went across to T, I'm going to use the self-same point over there, which is minus 7, 6. So on T, I get minus 7, 6. Okay, what has happened here? Have the y values changed at all? No, only the x values have changed. So if we think back, if the x values change and the y stay the same, it is a reflection about the y-axis. Very good. Let's have a look at our next one. The next one wants us to go from S to T. All right? It wants us to go from S to T. Now, is that a glide transformation? Well, sort of looks like it. The one side stays the same and moves upwards, doesn't it? Sort of, the long side stays there and it moves upwards. But are the short sides both in the same direction? Is the long side pointing left and the short side pointing down to the bottom? Let's have a look at the diagram and double check it. I'm just going to rub out my scribbles from earlier so we can see this. Well, there's my short side there. And there's my short side there. Goodness, my short side was at the bottom on S and now it's the top on T. Oh, what's happening to my hand? It is reflecting. And yes, it looks like it's reflecting around the x-axis. But once again, I'm going to list a point and double check it. So I'm going to take that point on T and the corresponding point on S. The point on T was minus 9, 2. The point on S is minus 9, minus 2. All right, what's happened here? The x's have stayed the same and the y's have changed. So, yep, it is a reflection about the x-axis. And why are we doing this in words? Is because that's what they wanted us to do. We're describing the transformation in words. Right, our last one. Our last one is going from Q to T. And I'm just going to rub out these scribbles so that we can see exactly what's going on. Right, we're going to go all the way from Q through to T. From there, all the way to there. Now, is that a double reflection? Is it a rotation? I think it might be very useful to list the points in their respective positions and just double check that. Here on the sharp end, that is the point -9, 2. And that is the result of that point over there coming across somehow. And this is the transformation we're trying to work out. That was the point 9 minus 2. Goodness me, looks like the signs have changed. Let's have a look at the point opposite the longest side. And that's what I mean when we have to use corresponding vertices or corresponding sides. Biggest angle, opposite the biggest side always. In triangle Q, this point over here is -6, 7. So -6, 7. I've made a mistake there. It should be 7 minus 6. So let's rub that out and do it. From 7 minus 6, that is translated and it's become -7, 6. So yes, you've spotted it already, exactly the same values, just the negatives have changed. Just for luck, we're going to do the last side, the last vertex. Now, the vertex in triangle Q is the vertex 9 minus 8. And 9 minus 8 has popped across and become -9, 8. So, what is this telling us? It's telling us that the values of x are staying the same, but the values of the values of x are changing sign and the values of y are changing sign, but they're staying the same essentially. Now, is that a reflection around the x-axis? No. Around the y-axis? No. Could it be around the line y equals x? You might ask. Well, has the x become the y and the y become the x? No. So what is our only other option? Yes, you're absolutely correct. It's a rotation of 180 degrees. So let's write that down. This would be a rotation of 180 degrees. Now, if you want it to be absolutely technically correct, it's a rotation of 180 degrees about the origin. Okay. Remember what we said at the beginning? In grade 11 and 12, we rotate around the origin. And for those of you doing AP Maths, things get really exciting and you rotate around all other kinds of points. Right, we're here at another question. And start off with the usual triangle, ABC, and let's see where this question takes us. All right, ABC, normal place, second quadrant, looking good. Numbers look a little bigger than usual. Something interesting is going to happen, I'm sure. Down to the question. Draw and label A dash, B dash, C dash, the image of ABC, under the transformation xy becomes -1/2 x plus 2, -1/2 y plus 1. Goodness me. This is a 2-in-1 transformation. It is multiplying by a scale factor as well as an element of glide across and in this case up. Now, in a question like this, it's really useful, for accuracy's sake, to list the points before the transformation and list the points after the transformation and then put that onto your graph. Those of you who's superb with mental arithmetic might like to do this directly. I'm going to do it so that I know I get it right every time. Well, we start with the point A, and I'm going to get the coordinates from the diagram. Minus 14, 8. And I know that that is going to transform to A dash at some stage. Let's get B and then C. Back to our diagram. B is minus 5, 8. And that will translate or transform to B dash. Now, something you've probably picked up on is that the y values of A and B are the same. Now, having a look at this question before I presented it to you, it became obvious to me that those points were specially selected. Something we need to watch out for with triangles is if we're going to have to work out the area, we're going to have a base and an altitude at right angles to each other. Let's just bear that in mind. Let's get the values for the coordinates of point C. C is the point minus 8, 2. Minus 8, 2. And once again, that will transform to point C. Right, let's work this out and see where we go. Negative a half times negative 14 gives us 7, and 7 plus 2 gives us 9. I'm just going to do all the x values first. Negative 5 times negative a half gives me 5 over 2. 5 over 2 is the same as 2.5. 2.5 plus 2, 4.5. Negative 8 is my x value for C. Well, negative 8 times negative a half will give me 4, and 4 plus 2 gives me 6. Right, the x values sorted out. Let's do the y values. Once again, it's multiplied by negative a half, and then we add 1. So, negative a half times 8 gives me negative 4. Negative 4 plus 1 gives me negative 3. Be very careful with your accuracy, and if in doubt, use your calculator. Might take a few seconds longer, but you definitely will get the marks. Negative 8 times negative a half gives me negative 4. Negative 4 plus 1, negative 3. As I said to you earlier, have a look at those two y values. They're the same. That means that A dash, B dash are going to lie in the same horizontal line. Maybe it's got something to do with areas. Point C, the y part. 2 times negative a half gives us negative 1, and negative 1 plus 1 gives us 0. Right, question finished? Yes? No. The question asked us to draw and label A dash, B dash, C dash. So we've got to take this information that we've now calculated and pop it back onto the Cartesian plane. Right, A dash, 9, negative 3. 9, negative 3. So over there is A dash. And that is at 9, negative 3. Let's look for our next point. B dash was 4.5, negative 3. 4.5, negative 3. B dash, 4.5, negative 3. The first side of our triangle. C dash was the point 6, 0. 6, 0. So what we've done now is we've drawn it and we've labeled it. That was C dash. Let's have a look at what this transformation actually was. Well, the triangle is shrunk because we multiplied it by a scale factor of 1/2. Now, if we remember, when we multiply by a scale factor of 1/2, not only do the sides decrease to half their size, but what happens to the area? Remember, it's the scale factor squared. So if it was, in the case of these two triangles, a scale factor of 1/2 from green to yellow, the area will be 1/2 squared, which is 1/4. And I'm sure it's obvious to all of you that 4 of those triangles would fit into that green one if I were to chop them up. Let's carry on with the questions. Part B tells us to describe the above transformation in words. Let's go back to our diagram and see if we can work that out. Well, what's actually happened? Yes, it has got smaller. What also has happened, have a look at the side that is parallel to the x-axis. AB is over there, with the sharp point pointing, the other bit pointing down, C pointing down. And when we did the transformation, A dash, B dash was there with the C bit pointing up. So it's actually reflected as well. So it's become smaller, it's reflected, and what else has happened? There's been an element of glide in it as well. Absolutely correct. So if we look at this over here, that whole big formula, the x became a negative and the y became a negative. Now, what kind of transformation is that? Is it a reflection, as I previously indicated, or could it perhaps be a rotation? Well, the x's and y's didn't swap. So it's not a reflection around y equals x. The x's and y's stayed in the same place, so it's a rotation of how many degrees? Well, it's 180. So let's go down to the bottom and write this out. Part B. It's a multi-transformation. That means multiple things have happened. Well, what has happened? The x and the y have negatives in front of it. So it has been a rotation of 180 degrees. Right. What else has happened? What is that 0,5 or a half doing there? Well, that indicates to us that it is multiplied by a scale factor of 1/2. In other words, it has got smaller. And there's a third bit to this. Yes, it has been moved 2 units to the right and 1 unit up. So it's moved 2 units right and 1 unit up. Wow. 3 things happened to that poor triangle from ABC to A', B', C'. It was rotated by 180 degrees, then it was shrunk by a scale factor of a half, and then it was shifted right and shifted up. Now, if you were to do those in 3 separate steps, let's say from A to A', to A double dash, to A triple dash, you'll land up with this one multiple transformation that we have. Having a look at the algebraic background to the actual transformation gave us the hints as to what this multiple transformation was. Because if we were just to look at the pictures, well, it's not a straight reflection or rotation or glide or scale factor. So looking at the algebraic bit really assisted us in this. Let's look at the last sub-question. What will the value of area triangle ABC 2, and that indicates they're looking at a ratio to area A', B', C', What will the value of the areas be? The ratios. Now, I know that you have already realized that ABC was multiplied by a half. The scale factor was a half. So the one triangle is 4 times larger than the other triangle. Let's go back to our original diagram and double check this. Well, if we take this triangle over here, ABC, what we can do is we can construct an altitude at right angles to the line AB. Wasn't that useful? Put there on purpose by the examiner. The length of AB is quite easy to determine. 1, 2, 3, 4, 5, 6, 7, 8, 9 units. The altitude, well, would be 1, 2, 3, 4, 5, 6 units. So what is the area of our triangle, the triangle ABC? Well, that's a half times 9 times 6. And yep, you all got it right. 27 square units. Right, and now we're going to find out the area of triangle A', B', C'. Well, I'm going to take A', B' as my horizontal line, and that is 1, 2, 3, 4.5 units. So A', B' will be 4.5 units, which, as we all know, is 9/2. I now have a look at my altitude, and there it is. Remember, that's why the examiners put A', B' horizontally. Well, that altitude is 1, 2, 3 units. So my altitude is equal to 3 units. So to conclude, the area of triangle A', B', C'. Well, what is it? Yep, it's a half times the base times the altitude, which in this case is 27/4 units squared. Now, isn't that amazing? Triangle ABC, 27 units squared. Triangle A', B', C', 27/4. Ratio 1 to 1/4. That's what we thought it was going to be, and we've just shown it. So no matter what happened to poor triangle ABC, it was reflected, rotated, still it was multiplied by a scale factor of 1/2. So the area was 1/4 of the original. I'm just going to write that out formally. So my answer to part C is the area of triangle ABC to the area of triangle A dash, B dash, C dash is 1 to 1/4. But as we all know, we shouldn't have fractions when we write ratios, which is the same as 4 to 1. And that's exactly what we thought it was going to be. Well, there we have it. Transformations in a nutshell. What I'm going to do is I'm just going to summate what we've done today. Right, what are transformations? Remember the word? It's transform. It's to transform a shape, a point, a line segment, something like that. How do we do that? Well, we started off with reflections. There was reflections. We had reflections in the x-axis. And that's when the y values changed sign. We had reflections in the y-axis, top to bottom or bottom to top. And that is when the x values changed. We had reflections in the line y equals x. And that was one when the x became the y and the y became the x. And we also, in doing some of the questions, we picked up, we could also get a reflection in the line y is equal to minus x. Let's just write out those transformations. In this case, xy became x minus y. With the y-axis, xy became minus xy. With the line y equals x, we had xy becoming yx. And with the line y equals minus x, we had the line becoming minus y minus x. So those are the reflections that we've discussed today, the 4 of them. In some extreme cases, there might be a reflection around a vertical line, x equals 2, or a horizontal line, y equals 5. But you're more likely to get that next year. After reflections, we looked at rotations. Now, with rotations, we remember that we have positive or anti-clockwise, and we had negative or clockwise rotations. And we could rotate 90 degrees. And remember, we like to use a little diagram to help us remember exactly what happened. We could also rotate 180 degrees. And with the 180 degree rotation, our xy became minus x minus y. And if you remember, if we put two 90s together, we got the 180. All right, remember 180 clockwise or anti-clockwise makes no difference. 270 clockwise is the same as 90 anti-clockwise. That was rotations, always around the origin. The last little thing we had was a scale factor. And a scale factor, all that means is that it's getting bigger or smaller. All we do is we multiply every single point by a scale factor. To summarize, a scale factor of k xy would become kx ky. And in most cases, our area from xy to the transformation would be k squared. All right. Transformations in a nutshell. Get out there, be the best you can be, and have fun.